Welcome to part 4 of week 4 of pre-calculus. Our topic today is rational functions. Let us first of all agree that whenever we draw these arrows on graphs, what they mean is that the graph approaches a certain line, and the distance between the graph and that line can be made as small as one wishes. That, by the way, doesn't preclude the situation when the graph intersects that line, even infinitely many times. Once again, the situation when you have a graph approaching a straight line in a way that the distance between the graph and that straight line can be made as small as possible, as small as you wish, will be denoted by these arrows on the graph. Now a little bit about limit notation. We already talked about limits when we studied the end behavior of polynomials, and we had this notation: f at x going to infinity and x going to infinity. Remember, that means that x approaches infinity or increases without bounds, either to positive infinity or to negative infinity. But now we may specify x approaches negative infinity, for instance. That means x is a very large negative number, and it can be made as large as possible by absolute value and negative. We will also consider limits at finite points, and we will use this special notation: x approaches a from the left and x approaches a from the right. That'll denote the situation when the values of x concentrate as close to a as you wish, but stay to the right of a. Or likewise, when x approaches a from the left, the values of x concentrate as close to a as you wish, but stay to the left of a. This notation allows us to define the idea of vertical and horizontal asymptotes. A vertical asymptote is a vertical line, x equals a, for which we have one of the following things: either limit to a limit at a is infinity, or the limit from the left is infinity, plus or minus, or the limit from the right at a is infinity. In the pictures above, for the graph of 1 over x, we clearly have limit of 1 over x at 0 from the right, positive infinity. When values of x approach 0 from the right, the corresponding values of the function 1 over x approach positive infinity. Already that fact alone makes the line x equals 0, which is the y-axis, to be the vertical asymptote of the function 1 over x. Already this implies that x equals 0, which is the y-axis, is a vertical asymptote of 1 over x. But of course, you can also note that limit at 0 from the left of 1 over x is negative infinity. And that also implies that x equals 0, the y-axis, is a vertical asymptote. For the function 1 over x squared, whose graph is on the right, we also see immediately that the limit of 1 over x squared, either from the right or from the left, the two-sided limit, is positive infinity. So x equals 0 is a vertical asymptote. Now, a horizontal asymptote is a horizontal line of the form y equals b, for which b is the limit of f at either positive infinity or negative infinity. In other words, it's such a straight line which is horizontal, y equals b, that the graph of f approaches that line either for very large x is positive or for very large x is negative, or both. That is an example of a horizontal asymptote. Our graph approaches that line at positive infinity. For the two functions above, we immediately see that in both cases, y equals 0 is a horizontal asymptote. Why is that? Well, that is because a limit at, say, positive infinity is 0. You can clearly see that when you divide 1 by increasingly larger and larger positive numbers, you get numbers that are closer and closer to 0. In fact, the limit at negative infinity is also 0. Right? When you divide 1 by 10, by negative 10, by negative 100, by negative 1000, by negative 1 million, you get numbers that are smaller and smaller but negative, but smaller and smaller in absolute value, and so they're closer and closer to 0. So this fact implies that y equals 0 is a horizontal asymptote. Of course, exactly the same argument applies to the other graph as well. The limit at infinity, either positive or negative, of 1 over x squared equals 0. So y equals 0 is also a horizontal asymptote for this graph, 1 over x squared. Again, these are two very important concepts. Vertical asymptotes, that's where your function blows up. That's where the limit is infinite, either two-sided or a one-sided limit. And a horizontal asymptote, that's a special horizontal line to which your function approaches at either positive or negative infinity. Let us look at some example. This problem is asking us to describe the end behavior and local behavior of the function graphed in the figure. Let's call it f. And it looks like we have a vertical asymptote at the point 2, and we might be very precise here. We can say that limit of f at 2 from the right is positive infinity. That's what it seems. And that limit at 2 from the left appears to be negative infinity. So that means x equals to either of these, not necessarily, not both. You don't need both of these. Either of these implies that x equals 2 is a vertical asymptote, VA. Now it also appears that y equals 4 is a horizontal asymptote. Why is that? That is because a limit at, say, positive infinity appears to be 4. It looks like our graph approaches the horizontal line y equals 4. And actually, it also approaches that line at negative infinity. It doesn't matter if it approaches that line from above or from below. As long as we have that limit, it so appears, we conclude that y equals 4 is a horizontal asymptote, HA. And here again, either of these two implies that x equals 2 is a vertical asymptote. And the same here. Either of these two implies that y equals 4 is a horizontal asymptote. All right, in the next example, we need to sketch a graph of the reciprocal function shifted 2 units to the left and 3 units upward. Then we need to identify the horizontal and vertical asymptotes. Well, if I draw the coordinate axis here, the reciprocal function 1 over x, remember, has one vertical asymptote, which is the y-axis, and one horizontal asymptote, which is the x-axis. So when we shift the graph 2 units to the left and 3 units to the right, we will shift the vertical asymptote 2 units to the left, and the horizontal asymptotes will be shifted 3 units upward. So this y-intercept is 3, and this x-intercept is -2. And then the graph will look exactly like the reciprocal function. And of course, the equation of this graph is y equals 1 over x plus 2 plus 3. The plus 2 instead of x makes for the horizontal shift by 2 units to the left, and the plus 3 makes for the vertical shift by 3 units upward. And again, x equals -2 is a vertical asymptote, and y equals 3 is a horizontal asymptote. All right, let us finally define the concept of a rational function. To put it simply, a rational function is a ratio of two polynomials. So whenever we have two polynomials p and q, p of degree m with coefficients a0, a1, am, and q of degree n with coefficients b0, b1, bn, where of course q is not allowed to be the zero polynomial. The function that is their ratio is called a rational function. And of course, in particular, polynomial functions and linear functions are examples of rational functions. In the case when polynomial q is 1, the denominator equals 1, you get a polynomial. And a linear function is a special case of a polynomial. So polynomials and linear functions are examples of rational functions. Unlike, however, polynomials and linear functions, rational functions need not be defined on the entire real line. They will be defined on the entire real line minus all those points where the denominator q is 0. So the domain of a rational function is the entire real line minus the zeros of the denominator. For example, let us find the domain of this function x plus 3 over x squared minus 9. If we do simple algebra here and write x plus 3 over x squared minus 9 as x plus 3 over x plus 3 times x minus 3. Now cancel the x plus 3, not forgetting to say that x plus 3 must be non-zero. Which is equivalent to x being different from -3. It's interesting to note how the graph of this function will look like. X plus 3 over x squared minus 9, and as we agreed, that is just 1 over x minus 3 if x is different from -3. Well, compare the graphs of f and the function 1 over x minus 3. Let's draw both. the function 1 over x minus 3 is simply the reciprocal function shifted to the right by 3 units. But the graph of f will look slightly different. We now have to exclude the point where x equals negative 3. As you see, they're really not the same. Their domains are different, and their graphs are different. Now, suppose that some number a is a root of the denominator, but is not the root of the numerator. It's easy to see that in this case, the limit of our rational function will be infinity. And so the vertical line x equals a will be a vertical asymptote. But why is this limit infinity? Well, if a is a root of q, as x approaches a, q approaches to 0. But p at x approaches some finite non-zero number. And when you divide a number that is not close to 0 by numbers that are closer and closer to 0, the ratio will of course be closer and closer to infinity. Hence the following theorem. If x is not a root of the numerator, but is a root of the denominator, the vertical line x equals a is a vertical asymptote of the graph p over q. We could see this in our example. Number 3 is a root of the denominator. But not a root of the numerator. So when you compute the limit of f at 3, the numerator x plus 3 will be approaching 6, whereas the denominator x squared minus 9 will be approaching 0, 3 squared minus 9. So you're dividing numbers that are closer and closer to 6 by numbers that are closer and closer to 0. Of course, the ratio is infinitely large. That is what we see on the graph. X equals 3 is indeed a vertical asymptote. That is what this theorem says. Let's try another example. Find the vertical asymptotes of this graph k of x equals 5 plus 2x squared over 2 minus x squared. So in our situation, the denominator q is 2 minus x squared, and it's 0 whenever x is 1 or negative 2. Note that neither number, neither 1 or negative 2, is a root of the numerator because the numerator doesn't have any real roots at all. 5 plus 2x squared is at least 5, so it's strictly greater than 0. So neither 1 nor negative 2 is a root of p, the numerator. So we have that both are vertical asymptotes. X equals 1 is a vertical asymptote, and x equals negative 2 is a vertical asymptote. But now here is a more interesting situation. What happens if x equals a is a root of both the numerator and the denominator? We know that by the factor theorem, that implies that x minus a is a factor of both p and q. So a being a root of p implies that x minus a is a factor of p. Well, that means, by the very definition of what it is to be a factor, that polynomial p can be written as x minus a times some other polynomial, let's call it p1 of x. And the same is true about the denominator q. Since a is a root of q, x minus a is a factor of the denominator q, so q may be written as x minus a times some other polynomial q1. So what we have here is this. And now the interesting move. Because x approaches a, x is not exactly a. We can cancel this by x minus a. It's safe. X minus a is not 0. So the cancellation by x minus a is safe. And I get that the limit of p over q equals limit of whatever those two polynomials P1 over Q1 were. And now, if it so happens that A is neither a root of P1 nor a root of Q1, this limit of the ratio of P1 over Q1 is simply the ratio of the values of P1 and Q1 at that point A. In that situation, the line x equals A will not be a vertical asymptote because the limit will be finite. In fact, one example of this we already had. We canceled by x plus 3, which was safe. Of course, we could do this only provided that x is not equal to negative 3. And we have this excluded point on the graph, but no vertical asymptote at negative 3. This situation is very special because this number A has two special properties. First, the function is not defined at A because A is a root of the denominator. You can't divide by 0. For example, I couldn't compute the value of f here at negative 3. Formally, I would write negative 3 plus 3 over negative 3 squared minus 9, that is 0 by 0, but 0 by 0 is nonsense. So I could not have written that. The function is not defined at negative 3. Yet, despite f being undefined at this point A, the limit at that point exists and is finite. It's this value P1 of A over Q1 of A. A point like this is called a removable discontinuity. There's a special name for situations like this. A removable discontinuity. That's a point where a function is not defined, yet the limit at that point exists and is finite. Let us look at this function f, which is x squared minus 1 over x squared minus 2x minus 3. If we factorize the numerator and the denominator, it will be x minus 1, x plus 1 in the numerator, and x minus 3, x plus 1 in the denominator. And note that provided that x is not negative 1, which it can be, because at negative 1 the denominator is 0, it's safe to cancel. We get a function that has a vertical asymptote at 3. That is because 3 is a root of the denominator, but not a root of the numerator. And indeed, we see that x equals 3 is a vertical asymptote. But there is also a special point on the graph, which this function, x minus 1 over x minus 3, wouldn't have. But our function is not x minus 1 over x minus 3. Our function is x squared minus 1 over x squared minus 2x minus 3. They're different. It will have a removable discontinuity at the point -1. And this discontinuity is removable because if I were to compute the limit, at -1, of our function f. Our function f is x minus 1, x plus 1, over x minus 3 times x plus 1. Again, our usual argument. X is close to -1, but x is not exactly -1. So x plus 1 is not exactly 0, and the cancellation by x plus 1 is safe. So this limit is simply -1 minus 1 over -1 minus 3, which is -2 over -4, and that is 1/2. It exists and is finite. The limit that our function f approaches when x approaches -1 from either side is 1/2, even though at the point itself the function is not defined. You can clearly see here why this terminology makes sense. Why it's called removable discontinuity, right? Because if we consider the function say g of x, which is f of x when x is not -1, and 1/2 if x is -1, then we would remove the discontinuity at the point -1. So the important upshot here that I would like you to remember is that not every zero of the denominator q of x is a vertical asymptote. Of our function p of x over q of x. In this example on the left, the denominator has two zeros, 3 and -1. 3 is a vertical asymptote, but -1 is not. All right, let's take a break here.